How do meshing errors impact FEA stress analysis? Imagine trying to predict how a bridge will hold up under heavy traffic, but your calculations are off because of tiny mistakes in how you divided the structure into parts. That's what meshing errors can do in finite element analysis. When engineers perform stress calculations, they break down complex parts into smaller, manageable pieces called elements. The way these elements are shaped, sized, and distributed makes a big difference in how accurately the analysis reflects real-world behavior. If the mesh isn't done carefully, the results can be way off. For example, if the mesh is too coarse, it smooths out stress variations and might miss the highest stresses near sharp corners or load points. That could lead to underestimating where a part might fail. On the other hand, if the mesh is too fine in some areas but not near stress concentration zones, it can give misleading results. One common problem is lack of mesh convergence. This means that as you make the mesh finer, the stress results should stabilize. If they don't, the analysis isn't reliable. You might see stress values that keep changing or get larger as you refine the mesh. That's a sign that the mesh isn't capturing the true stress state. Stress singularities are another issue. These happen at sharp corners or points where the geometry causes the theoretical stress to go to infinity. But in real life, parts always have some small radius or fillet to avoid this. Ignoring these singularities can lead to exaggerated stress predictions that don't match actual conditions. Other meshing errors include using the wrong type of elements. Linear elements are simpler but less accurate in areas with complex stress patterns. Higher-order elements, like quadratic ones, better capture nonlinear stress changes. Poor quality elements, such as distorted shapes or bad aspect ratios, can cause numerical inaccuracies. Not enough mesh density near stress hotspots can also hide critical stress peaks. Sometimes, to save time or resources, engineers coarsen the mesh, but this can sacrifice accuracy. To avoid these issues, it's good practice to perform mesh convergence studies. This involves refining the mesh step by step until the stress results stop changing significantly. Using higher-order elements in complex regions helps improve accuracy. Modifying the geometry to remove sharp corners or adding fillets can prevent stress singularities. Ensuring the mesh is made of well-shaped, properly connected elements is key. Checking deformation patterns and comparing results with experimental data can also help confirm the mesh is appropriate. In mechanical engineering stress calculations, meshing errors can lead to underestimating stresses, risking unexpected failures, or overestimating them, causing overly conservative designs. Proper meshing makes sure your stress analysis is reliable, helping you design safer, more efficient structures and components.